Okay, we're going to continue working on the next questions. So for question 2, we have a statement qxy means that x times y it's equals to x plus y, and we're allowing any integers to be used for the variables x and y. So are they true or not? So the first one says q22. So what we have to do is simply just say if we have 2 times 2 and 2 plus 2, are they the same? And the answer, of course, is yes, because 4 is equals to 4. So the first question, it's true. The second one is 2 times 10 equals to 2 plus 10. And the answer is no, because 20 is not the same as 12. So the second one is false. Now, the next one, now we have quantifiers. So the question is it true that for every y, 2 times y, it's equals to 2 plus y for any y? Well, if you want to show that it's true, you have to make sure that this is true for any y. But if you want to make it to show that it's false, all you have to do is choose one y that makes it false. And there are many different values of y you can choose here, because this statement is false for most y. So even if you just say if y is equals to 1, then 2 times y is equals to 1, and 2 plus y is equals to 3, which are not equal. So it's definitely not true for all y. Next one, there exists some x and some y such that q of xy is true. Well, we already know from part A that q22 is true. So if x is equals to 2 and y is equals to 2, that gives you some pair of x and y that makes it work. So that makes the existential statement true. The next one says for every y, there's some x that can make this true. Okay, so no matter what y you give me, I can always find you an x that makes it work. So x times y is equals to x plus y, and y is given. So I have to figure out if for any possible value of y, I can find an x that makes this equation true. So what I do is I try to solve for x given y. So I would say x times y minus x is equals to y. Then I'm trying to isolate like this. And then finally, I can say that x is equals to y divided by y minus 1. So whatever value of y you give me, I compute this quotient, y divided by y minus 1, and set that to x, and then this works out. But there's a problem. The problem is that these variables are not fractions, but they're integers. So if y is, let's say, 2, so y is 2, then 2 divided by 2 minus 1 is, it's 1, so then x is 2, which we already know when y is 2, x can be 2, that works. But if y is 3, then 3 divided by 2 is 1/2, and 1/2 is not a valid value for x. So that means that when y is 3, then this statement you cannot find the correct x that makes it work. And there are many other values for y that will make x not legal. So for example, if y is 1, then you're trying to do 1 divided by 0, which is also not possible. So anyway, we can do many different things. So for example, if y is 3, then x is equals to 3/2, which is not an integer. So when y is 3, that does not exist an x that makes it work. So this is false. And then finally, it says for every x and every y, qxy is true. Well, we already know from part B that q210 is not true. So that there's no way that you can make it true for every single pair of x and y. So this is also false. So if you want, you can say C part B, because part B gave you an example where that doesn't work. Okay, so that's how you do question 2. Okay, now I'm gonna go and erase this, and then I'm gonna scroll down and do questions 3. Okay, so this question is very similar to the one that is in the midterm, right? So again, the domain is integers. You have these predicates. E is E of n means n is even. P of n means that n is prime. B means that B is the divisor of A. So the first one says an integer n, it's even if and only if there exists an integer k such that n is equal to 2k. So for all n, if n is even, if and only if there exists a k such that n is equal to 2 times k. So that's part A. Part B, an integer is prime if and only if n is greater than 1 and the only divisors of n is 1, minus 1, n, and negative n. So for all n is prime if and only if, okay, if and only if what? N has to be greater than 1 and the only divisors of n, it's 1, minus 1, n, and minus 1. So what do we say? We say, if you give me any divisors d, then d is the divisor of n if and only if d is equals to 1 or d is equals to minus 1 or d is equals to n or d is equals to negative n. So now I have to close all my brackets. Okay, so let's review this because this one's a bit complicated. So for every n is a prime number if and only if something. What is this something? N has to be greater than 1 and the hard part is the only divisors of n is 1, minus 1, n, and negative n. So that when you say the only, that means no other numbers are divisors. So basically you have to say for any number, d, if d is one of these 4, then it's a divisor. But vice versa, if it's you have a divisor, then it must be one of these 4. There are no other things that can divide n. And then finally, C, every even integer greater than 2 can be expressed as a sum of 2 primes. So for all n, if n is even and n is greater than 2, okay, so this says every integer even greater than 2, then it can be written as a sum of 2 prime. So I need to say there exists 2 other number called it P1 and P2 such that P1 is a prime, P2 is a prime, and n has to be P1 plus P2. Okay, there's a sum of 2 numbers, each of those are prime. Let's close out the brackets. Okay, so again, for every number, if it's even and greater than 2, then you can find 2 numbers that are prime, they're both prime, and adds up to n. Okay, that's how you do this problem. Okay, let's go to the next one. Okay, so we have a domain, we have Sn, just the numbers 1 to n, and S3, for example, is 1, 2, 3. So give an example of one-to-one function that is not onto. Okay, so I have 1, 2, 3 in S3. I want to map it to 1, 2, 3 in S3. I want to be able to make a one-to-one function Okay, 1 to 1, remember, means that no two arrows goes to the same spot. So this is a 1 to 1 function, but it's also onto. Can I actually make a function that is 1 to 1 but not onto? The answer is no. It's actually impossible because the two sets have exactly the same size. So when you try to make it, the only way you can make it not onto is by having more than one arrow going to the same place. So this is actually impossible. The next question says, give an example that goes from S4 to S3. Well, that's impossible. So for example, I can just add one more arrow from 4 to 3, and now this is not 1 to 1, but it is definitely onto. Okay, so that's the answer for B. And then for C, give a function that is bijective. So if I just say h of 1 is equals to 1, h of 2 is equals to 2. So in other words, I just take the number and map it to itself. That's both injective and surjective, 1 to 1 and onto. And then finally, this is maybe a little bit trickier. Let Bn be the set of all bijective functions to S, from Sn to Sn. What is B3? B3 says that you can go from 1, 2, 3 to 1, 2, 3, and you want to know what are all the possible bijective functions. Well, bijective means that 1 has to go somewhere, wherever it might be. 2 has to go somewhere, but it cannot go to the same place that 1 goes to. And 3 has to go somewhere. And basically, if you think about it for a bit, the first one can go to anywhere, the second one can go to anywhere but the first one, and the third one can go to anywhere but the first two. So the total number possibility is 3 times 2 times 1, which is 6 for B3. And in general, the first one when you go from Sn to Sn, the first one has n choices, next one has n minus 1 choices, n minus 2 choices, and so on. And it's basically n factorial, or the number of permutations. I'll stop here and I'll continue on in the next video.